Now things are even better than I let on last time. So I said that this curl thing is a check. It's a check to see, hey, can I find an anti-gradient for this vector field? In principle, the curl only tells you, maybe or maybe not. But if the vector field is defined everywhere, then the curl check is completely sufficient. If it has curl identically 0, then it's a gradient vector field, and you'll be able to find an antiderivative. So one way to find antigradients is to just do it manually. We integrate each component, and then we try and match the answers up. We have to keep careful track of what constant means when we do this. So here's a vector field in 2D as an example. F of xy is equal to 3x squared plus y squared, comma 2xy minus 4y. And I say that it has curl 0. To check that it has curl 0, we would calculate the x derivative of 2xy minus 4y, and then we would subtract the y derivative of the first component, 3x squared plus y squared. And that would be the x derivative of 2xy is equal to 2y, the x derivative of minus 4y is 0, and then we would get minus the y derivative of 3x squared, and minus the y derivative of 2y, that's 2y. So this vector field does indeed have curl 0. To find an anti-gradient, what we would say is, well, if this is going to be a gradient vector field, then this thing on the left has to be the derivative of a function with respect to x. So I find an antiderivative of it with respect to x. An antiderivative of 3x squared with respect to x is x cubed. An antiderivative of y squared with respect to x is xy squared. Both of those are functions where if I take the derivative with respect to x, I get 3x squared plus y squared. But I must remember that there's going to be a constant here. And this constant is not actually constant. It's just something that's constant with respect to x. If I change y, it's still allowed to change. And so I have to remember that this is only constant in x. It's still allowed to depend on y. Similarly, for the bottom one, I want to take the antiderivative of 2xy minus 4y. If I take the antiderivative with respect to y, an antiderivative of 2xy with respect to y is x times y squared minus y squared minus 2y squared. That's an antiderivative with respect to y, and then we also have to have a constant. But now it's something that's constant with respect to y, it's still allowed to depend on x. And then we're trying to match these up. On the top, we've got x cubed plus xy squared plus something that only depends on y. On the bottom, we've got xy squared, that matches up. We've got minus 2y squared, and something that only depends on x. And what we're trying to do is we're trying to match up something that depends on both of them, something that depends on x, and something that depends on y. And that's the main method we have. We figure out what the constant parts are by looking at the other antiderivative. Here, one of our antiderivatives only told us that we had a constant that depended on y, but from the other one, we find that that should be basically minus 2y squared. Similarly, one of the antiderivatives told we had a function that depended on x, but it matches up with the part that's x cubed from the other antiderivative. So putting the answers together, we get x cubed plus xy squared minus 2y squared as our anti-gradient for this vector field. We always go through this procedure, whether it's in 2D or maybe in 3D. We take antiderivatives of each component and we try and find a simultaneous answer that tells us about which constants go with which when we go through.